All right. Thanks for joining this Elisa seminar. Today we have Sebastian from Linutronix giving us a talk on real-time Linux. So Sebastian, take it away.
Okay. Thanks everyone for having me here. I would like to give a talk on how to not break preempt RT. We're getting close to get it mainline, so I want to start why do we try to mainline it in the first place? The reason is simply that we would like to spend less time on integrating it into every release and spend more time in polishing it and getting it to work better as far as possible. In the early days, we spent a lot of time to integrate it. Sometimes we had like 2, 3, or even more releases in between before we were able to have a working RT kernel. And with getting the code mainline, the changes that we need to integrate vanish because they are already integrated and we don't need to care that much about them anymore. While the code is upstream, other people are aware of it and changes are high that they are not going to break it accidentally. And right now, the time I need to make a new upstream release is kind of somewhere between the 2 weeks to 3 until the RC1 gets out. And before that, it took a few weeks until we had something that looked like working. And this time here is mostly gone. Once the thing is completely upstream, we could also have automated testing against the upstream tree. So we don't need any out-of-tree patches anymore. And this could enable us to start testing against Linux Next before we see regressions in the new upstream kernel. So this could also bring us ahead in terms of testing. And while it's upstream, it may attend or attract more people to start using it or looking at it. Now, what is RT doing? From RT perspective, we don't care mostly about each and individual subsystem. The focus is mostly on the user end. The application that the user is writing should be able to be scheduled as soon as possible and as long as it requires. So we don't focus on in particular subsystem like networking or I2C. We basically want to remain in user land once the user asks us so by a timer, an interrupt, or whatever the means are. The goal here is to have a low latency between the interrupt, the request, the scheduling, and the amount of time that is spent until the user task is active. In general, it's easy. The things that forbid us to do so are non-preemptible contexts, like where preemption itself is disabled or where interrupts are disabled. In all these contexts, we don't see the request to schedule that, and we can schedule in this time frame. We do lots of things to make it possible. One of the first things, or the obvious changes, is the locking. While spinlock-T and RW-lock are locks that are blocking, and spin while the lock is occupied, the RT changes it to have a similar semantics to a mutex. So basically, instead of spinning and waiting for the lock to get freed, RT basically takes a nap. It's similar to a mutex, but not quite. The differences are, for instance, that the state that we have is preserved. Basically, if the type of the state is changed before acquiring a lock, we preserve it. Non-RT or mutex-T will basically overwrite it, and after the lock has been acquired, it will be the state running. So this is not something we can do. Another thing is that we don't migrate to another CPU while the lock is occupied, after the lock has been acquired. The thing is that a non-RT, the preemption is disabled, which forbids us basically from migrating to another CPU. And we have to preserve the semantic. So this is another piece of the puzzle. Even while the CPU is being shut down, it's delayed basically for that reason until we release the lock. So again, here the semantic is preserved. And if the lock is acquired by another task and we have to sleep and wait for it, RCU won't complain and say that we are in RCU read lock sections and forbid us or complain, because this is usually not allowed to schedule while within RCU protected section. Yes. So basically the lock owner can always be preempted of those two locks which are non-spinning on preempt RT. This hurts preempt performance at some point, because sometimes it can happen that a new task gets on the CPU and gets blocked on the same lock like everyone else. And then new tasks that are runnable also block on the same lock. And the scheduler has little knowledge who to run, because everyone blocks at some point very quickly. For that reason, we introduce lazy preemption, which is kind of preempt disable, but it allows to schedule the RT tasks, which are the important ones, while sched order still has to wait for it to happen. The next thing, since the locks are preemptible and don't spin, we need to get out of the hard interrupt context where preemption and interrupts are disabled. And for that reason, we have interrupt handler which are threaded, basically all of them. This is the same behavior we have as with thread IRQ command option. So basically all interrupts are threaded and can sleep while spinning, while waiting for a lock. Handlers which don't want this for one reason or another need a special flag to mark it. One example is the timer interrupt, and perf is another one. The timer is actually easy to explain, since if the timer needs to wake RT task, we don't want to wait it for in a threaded context, which will add additional latency. Perf, for instance, needs to run with disabled interrupts in a hard IO context, because it wants to gather the perf counters as soon as possible and not taint them with additional overhead. So basically, most drivers says ATA or sound, whatever, is fine being threaded. And the exceptions are the few just mentioned. There's also code like in GPIO for interrupts, which are GPIO controllers, which are also acting as an interrupt controller. And those things have also to run in hard IO context in order to be able to wake other drivers from the hard IO context. So it's basically an interrupt controller which needs to preserve its semantics. After the threaded interrupts, we also have SoftIQ context, which is preemptible. And this helps us that the SoftIQ work that is being raised, like by network driver, is handled within the interrupt thread. So if the interrupt thread is with a higher priority, it can also handle its bottom down work with the elevated priority. So basically, non-RT handles SoftIQ after all interrupts exit, and then there's the SoftIQ part which works with enabled interrupts, but still preemption is disabled. And on RT, the same thing works basically after the threaded handler exited. Then the SoftIQ thread, then the thread continues to work on the SoftIQ work. This works basically in the same way. The one problem is that if SoftIQs are raised from non-threaded context, the problem here is that we cannot simply execute the work there, because we will punish an innocent task that has nothing to do with it. For that reason, all those work has been moved to KSoftIQD, where the remaining work is being proceeded. The one problem here is that once case of EQD is active, everything else that follows is being handled in case of the EQD. The reason for that is that it acts as kind of as a prevention for denial of service attacks. Basically, if networking is doing a lot of work, at some point it will hand over to case of EQD, because this one is the only one that is preemptible after a while. Otherwise, the user would not be able to attach the system. The HR timers on non-RT are usually invoked also in hierarchy context, which we move most of them to the threaded context. Basically, it runs in its thread of its own. A few of those are marked as mode hard for those which need the hierarchy context for its execution. One example is, for instance, the watchdog timer, which sees or tries to check if the CPU is still active or is locked up. If this would be run as in a thread as part of the SoftIQ, then it would never detect that as context switch is not possible. Therefore, we use this in this mode to ensure that the timer can recognize the context switch is not happening for a longer period of time, basically as mainline does. Also, it needs to be understood that the framework that can be used in hierarchy context is very limited, because most of the infrastructure is using sleeping logs. So there are limitations in place what can be done. One example is, for instance, clock Nanosleep, which is used from sleep, which is invoked from a user task, which if it needs to sleep for a specific period of time. If the task that is trying to sleep is an RT task, then it's going to be woken up from the hierarchy context basically immediately, as soon as possible, in order to reduce the latency. Every other task that is run at scat ADA will be delayed into the thread wake up. There is one thing called IOT Work, which is another thing that needs to be handled. And IOT Work was initially designed to handle wake ups from contexts where the usual wake up is not possible. One example is, for instance, PrintK would wake the thread in userland to notify that something has been written and that it can be pulled out from the buffer. But if this is going to be invoked from the scheduler itself, then it would be basically a deadlock, because the scheduler, while doing scheduling work, would need to wake a task which basically will recurse itself. Also, another example is everything from NMI that needs a wake up. It would try to acquire logs, which it cannot, because they can be occupied and NMI cannot wait. So for reasons like that, IOT Work was designed. And over time, a lot of other things have been put into IOT Work that are not very compatible with preempt RT. And for that reason, most of those things have been moved into its own thread. A few things that remain, though, is something like the no-heads kick, which is required to run with this in hierarchy context in order to observe if the CPU is idle or not. So it can make a decision if it needs to, if it can go to idle or not. And the PrintK wake up I just mentioned is the wake up klog thingy that doesn't actually care from which context it came from. So this is one of the things that is delayed into the IOT Work context on RT. Over time, what we got is, for instance, preemptible RCU. This is, as of today, already working in the preemptible kernels, and it's been initially designed for RT itself. Another thing as an extension that we need for RT is, for instance, the avoiding the usage of SoftIQ. In general, RCU uses SoftIQ to invoke its callbacks, which are basically freeing memory. And from RT point of view, we want to have as little SoftIQ work as possible. And for that reason, we use no SoftIQ options basically by default to move the callbacks in as much as possible from RCU out of the SoftIQ context, basically in its own thread, so it can be run, for instance, at a later point in time, not disturbing the RT work. With CPU isolation, it's also possible to move the callback thread to a so-called housekeeping CPU, and even further, it's possible to move the whole RCU machinery from one CPU to a housekeeping CPU, basically isolating the one CPU that is designed for doing RT work. Another detail we have enabled by default is, for instance, RCU boost. This is required in case one RCU reader gets preempted by a RT task over a longer period of time, which basically forbids RCU to complete its grace period, and therefore it cannot run any callbacks. And this could result in out-of-memory behavior over time. So basically, we try to avoid it by boosting the task out of its RCU section for better behavior. One thing that I try to explain here with some pseudocode is synchronization mechanism that is basically designed for spin until ready. The important part is that there is one task of one CPU doing basically waiting while the other task completes. The other task completes on the other CPU always, because it is at some point in a preempt disable section. And being in a preempt disable section means the task cannot go away from the CPU. It can continue. It will make progress. So in this example, active is set to 1, then it does something. Active is set to 0, at which point the thread on CPU 0 will see that it's completed and act. Now on preempt RT, the thing is different, because the preempt disable that was initially inherited from spinlock is no longer there. And the problem we get on RT is if the task with a higher priority preempts the task that it's waiting for, then it will never make progress, because thread 0 in this example will spin forever while waiting for active, and thread 1 on the other hand won't make progress because as part of spinlock it's bound to the single CPU, and this is basically a live lock for the system. It won't make any progress, and those things we need to avoid. We have a few examples of those in kernel. For instance, we have the timer code. As I mentioned earlier, the timers were running in SoftIQ, or HR timer was running with interrupts disabled. So both of them would make progress over time. While on RT, both of them are preemptible. Basically, it's possible that they don't make any progress. That means that Deltimer Sync could try to wait on a timer that is being run on the same CPU, and which avoiding progress. The same part is possible for sec counts. Basically, if one side is in the read sec count, in the sec count section as a reader, and the writer tries to wait until the reader is gone. This also won't happen for the same reasons. Both of them got a handshake mechanism in Del timer or on the sec count, which is more or less generic. And we added, for the timer solution is basically RT only, but for sec count we managed to get a solution which is used for RT only, but there is a version of it that can be also used on non-RT for debug. So, but the debug version ensures that it works perfect on non-RT, while RT uses the debug information to perform the handshake. While we changed a lot to make it possible, there are still a few primitives that remained as they are. For instance, local IQ still disables interrupts, and the bit binlock still disables preemption, and we have a few of those. The thing is that we don't have very much of those left, and the remaining few that are left in tree, basically I used over a small time frame or window, basically either adjusting passive view variables or hardware registers. So while scheduling in that window is still not possible, in general, it's a very, very small window where every other workaround or something like local T, where we would allow preemption on RT, is basically overkill because the window itself is usually just a few microseconds or even less. So it's not actually worth the effort. But we have local locative exactly for this kind of scheme where the locking on the non-RT kernel was designed and used with by disabling preemption or interrupts. So if needed, this is a good fit as a replacement. But all those things we have basically a log ordering that we managed to document and make part of the official documentation where we can pin developers to and let them hope to read it through and use it. So basically, we have, as a first rule, we have the sleeping logs, which is basically logs that always sleep while waiting on the log itself. This is basically a mutex or a semaphore. As the next step in the nesting, we have these sleeping logs, which basically sleep only on preempt RT. This includes, for instance, the spin log T. And the last one in the section is the raw spin log T, for instance, which is always spinning no matter what. If there is anything like disabling preemption or interrupts on its own, then this basically counts as the last step, because raw spin log T also disables preemption and or interrupts based on demand. But this changes is basically meant that manually disabling interrupts is not the same as using spinlock IRQ, because while the former still disables interrupts, spinlock acts different. So this would basically work on a raw spinlock T, but spinlock T is different here. So this log ordering needs to be preserved. So basically, when people try to write driver code or anything, and they have to decide if they need a raw spinlock T or spinlock T, the question is always what kind of driver it is and where does it run. Usually only the low-level code, like an interrupt controller or the timer low-level code and everything in that area requires raw spinlock T, because it still runs in the hard IO context with disabled interrupts and so on. Everything else is basically threaded at some degree and is perfectly fine with spinlock T. So in general, it's fine to use spinlock T and only to upgrade to raw spinlock T if for some reason the context is with disabled interrupts or preemption and needs to remain as is. As I mentioned earlier, the interrupts itself are already threaded, so it's usually infrastructure that we're talking about that needs to make that decision. This is a split from a normal RT kernel, which has the config while atomic options enabled, and someone tries to acquire a spin log in the preempt disabled section. So this is what this option gives us as a backtrace. So we see that something went wrong at exactly that spot, and this can be used to investigate further where something happened. So based on this output, which is cut out from the normal large one, so it basically says that preemption was disabled in function, and someone tried to acquire a spin lock later on. And the log itself is also written down, so this can be used to narrow down where it's coming from. And we have, for those with the memory allocation, we avoided most of those from the hardware context and allocation, and all those allocations that are made with disable preemption. So non-RT has this GFP atomic, which is used to allocate memory, like in the NAPI callback or so on. But the memory allocator itself is using sleeping spin locks all the way through, which basically means there can be no memory allocation within a preempt disable section or with interrupts disable on RT, and as a result also on mainline. However, it only counts for the context which are not also atomic on RT, and this is actually little. And while we work on it over years, we managed to avoid all of those from RT. And basically, we hope that it stays that way, simply because as of the nesting, as I mentioned earlier, and the memory allocators using sleeping spin locks, there's simply no way this can work. So a split like the previous one will be seen on RT each time, and allocation will be attempted. And to avoid always waiting for RT to spot it, we have something called ProofRawLoc Nesting. This is basically working on non-RT since a few releases. However, due to things like this in this example, where PrintK is involved, it's still not quite ready yet. What this option actually allows is to see on non-RT kernels where one acquired a raw spin lock and then acquired a spin lock T, which is sleeping on RT. So if this example, RCU would actually acquire and print something, at which point this backtrace is seen. So it basically says that we have an RCU log, which is perfectly fine. And then we nest further to the console log and the console owner. And then we get to the state where we have a raw log, and then we try to get a sleeping log. And this is the warning we get then. So this is one thing that we try to get up, to have some debugging output on kernels which run without RT. But since we are at RT, for the 6.0 kernel, I actually tried to get most of the bits upstream and RT enabled, but this actually broke down on the PrintK case. So to give you a short overview how this all works. So PrintK basically does a few things. The first part is actually the PrintK command gets a string as an argument. The string is then evaluated and it's put together, and then it's added to the buffer and saved, which is then used to print later the console or can be retrieved from the log buffer. Now, once this all is done, then the next step is the critical one. It's actually uses a console driver to do the printing. Now, the console driver, as a usual driver, is having the spin lock T for locking. But PrintK itself can be used from any context, like from the hardware context or from preempt disable region. So we cannot use the spin lock T in console driver then, because due to the lock nesting, it will forbid it. So an easy change would be to get the console driver to use a raw spin lock T. Now, to continue the example further, you can look at a serial UART driver, which can be used as the console. And at a reasonable speed, like L500 baud rate, it will take us roughly 86 seconds, microseconds to print a single byte. And to have a assuming a small message with 20 characters, it will take us over 1.5 milliseconds for the printing. A lot of RT systems out there require a latency of way less than a millisecond. And so this basically breaks it left and right. And for reasons like that, we cannot have the console log using a raw spin log, which will basically disable preemption and so on. And for that reason, we need to rework PrintK at some point to have everything that is added to the buffer in the first step. And then we need the console driver running in a thread or somewhere else. So it can be preempted while doing the slow printing work. So like the previous example with the console that takes a lot of time to print, all this is introducing long latency for the user if we are not able to schedule. And basically something like a preemption disabled region is what we call an atomic context. And assuming we have a list of items that we try to work, if the list is unbound, basically a lot of items can be added, like hundreds or thousands, then the longer we work or look over that list to pick as item, the longer the latency for the wake up becomes, because the atomic section gets increased in its runtime based on the number of items. And if the item that is being worked on also has long computation times, then the section with disabled preemption gets even longer and longer. Another thing is logs that are very heavy contended. And if one has a machine with 2 CPUs and both try to acquire the log, then it's basically only 2 CPUs fighting over the log. And the latency that the second CPU needs to acquire the log basically means the first one needs to be done with it and release it. And this time gets longer and longer if the number of CPUs increases. So basically with 64 CPUs, all of them waiting for the same log, it's basically something that increases the latency. And even if the section is small, the last CPU in the queue needs to wait the longest time. So this is also not optimal if the logs are that exposed. This is an example for clock Nanosleep that I try to show what it means to basically have an item or 2 or 100 in this example for the first. So this is an output from cyclic test. So cyclic test runs with an elevated priority as an RT task, and clock Nanosleep has to wake RT tasks. And in the first step, it tries to wake 100 tasks, and max is the maximum observed latency by cyclic test, and it reports 26, which is more or less the average latency that can be observed in idle on that particular machine. Now, if I go and try to wake 500 tasks simultaneously, then the latency increases visibly to 75 microseconds, and nothing else has been done on that machine, just the wake up of 500 tasks. If we go to 1,000 tasks, the latency increases to 374 microseconds. So at this point, it's visible that it's not good anymore, because if the required latency is like 100 microseconds or less, then this will completely disturb it. And with 5,000 wake-ups in the same period of time, it basically raises forbids scheduling the cyclic test for almost 4 milliseconds. So this is a clear example where it's not working. So in this example, we knew exactly where the latency is coming from. And there is a tool called RTLA, which is basically a tool for running, for looking for latencies in the systems. So like in the previous example, we see that for some reason we had a high peak in the latency. We don't know where it came from. So we could use basically a few tracing tools to narrow it down. And one example is RTLA. Daniel Bristol wrote it, and it's part of the kernel as of 5.17. And I added a link here where it can be seen basically in action. And it's slightly broken, but the message ID can be retrieved and pasted into lore. My point is basically the thread starts with a user that says that the old RT kernel was working fine, but the new has basically high spikes, and he has no idea what to do. And then Daniel pointed him to RTLA and told him, do this and see what happens, and send us please the trace. And the trace basically pinpointed where the error was coming from. So just wanted to make a small advancement for the tool, which is kind of nice. And the thread basically shows all the work from finding the spike in latency, what has been done to identify the culprit and how to work around it. Another thing that we do in RT and is more or less prominent when it gets to RT task and locking is basically priority inheritance, also called the PI boost. The simple thing is that we have one task and one lock, and another task, one set lock, but the task cannot run because it's got preempted. And it's kind of like the handshake mechanism I was referring earlier for the spin but wait. But it's slightly little more complex with priority inheritance or giving over in order to the task to make progress. So here is actually an example how it works. This is a cut down sketch tracer with all the important bits, and everything else has been left out. So basically, the thread locking A is running, and it acquired a lock, an important one. This lock is also required later by locking B. And so locking A, as it can be seen, woke up locking B, and since locking B's priority is higher, it got immediately switched over to locking B, while locking A was still running but couldn't make any progress. Now, locking B thread also needs that lock that is owned currently by locking A. And in order to do so, it hands over its priority, basically 79. The lower number is the higher priority, so it basically goes down to 0. And locking A increases its priority from 89 to 79. And the next step is that the scheduler switches over from locking B to locking A. And the point is basically locking B can do nothing in order to obtain the lock other than hand over the priority in hoping that with the higher priority, locking A can make progress. And as so, it basically does. And once locking A is on the CPU again, it does whatever it needs to do and releases the lock, and then it returns the priority back to locking B. So its priority is getting lowered from 79 to 89. Again, the lower number is the higher priority. And then the scheduler switches back to locking A. And this so-called PI, this is only possible with the sleeping locks and only with a few of those. So within the kernel, spinlock T and all of these kind of locks, like mutex itself as well, can make use of PI boost. RBSAM and RWLoc T, both of them are sleeping on RT, but they cannot make use of PI boosting all the way through. The thing is, the writer itself, there's only one of those, so those can be PI boosted, but RWSAM and RWLoc itself can have multiple readers, and we cannot boost multiple of them. So basically, you wait, and that's why I mentioned that it's only working to some degree. So it works for the writer, but it's not working for the reader. It can be used from userland. if for the pthread mutex lock, if the protocol is set to priority inherit, then it's basically using the same mechanism in the kernel. As I mentioned earlier, the SoftIQ context is problematic, and that's why we started to go for RCU to avoid it as much as possible. And in general, we try to avoid it as much as possible. The thing is that SoftIQ itself is basically anonymous, and no one really knows what is being run in there. So networking can upload work there in order to run with enabled interrupts and not disable interrupts for a longer period of time, basically, so preemption suffers a lot. But also we have timers, we have tasklets, and we have block IO, and we have everything else, which basically ends up as a big kernel lock, aka BKL, but it's only limited to a per CPU context. And the old RT releases tried to make all of those individual SoftIQs run in parallel, which worked at some degree, but it introduced many problems. So at some point, we switched to the same model that Upstream uses, and we basically use one lock to synchronize the SoftIQ on each CPU. And the reason or the outcome of it is that now the NetTX SoftIQ cannot run in parallel with the tasklet SoftIQ. It can be one or the other. And the result is that if the NetTX is busy and the tasklet SoftIQ is very important, then we have a PI boost if it's needed. But other than that, this tasklet has to wait until networking is done. And this is not optimal and has to be clearly worked on, but this is currently what we have. The best thing we can do right now is to minimize the SoftIQ load as much as possible, and if possible, to move the long-running SoftIQ work to one CPU while having the critical part on the other ones. Another problematic part is something that can be called like dispatching work for later use. One example are tasklets, which, well, they are around since long before we have threaded interrupts. So from what I can see is most of these can be moved to threaded interrupts and be dealt in a way that we have an owner, because otherwise tasklets are moved to a SoftIQ context where they run anonymously, and they cannot be made or preferred one against the other. Because with threaded interrupts, you can assign priorities and have one interrupt that is more important than the other. But with the tasklet thing, everyone vanishes into SoftIQ context and you don't really know who is doing what work. The same thing happens with the K work or the Q work thingy. And one prominent example is basically the TTY layer, where the UART receives a character and then pushes it into or attempts to push it into the buffer. But this happens via the worker. So one that relies low latency in serial communication over TTY will receive the character in the interrupt with elevated priority. But once it tries to stuff it to the TTY layer, it basically schedules the worker where all the elevated priority is last. And there's no way of steering or preferring one work over the other, at which point the user task that relies on input from the TTY layer has to wait until this get other task is run, basically hurting latency massively. So this is also one of the things that should be avoided in order to get good latency results. Another thing that is bad is from the worker point of view, if the worker is started on remote CPUs without any relation. Basically, if the RT task is run on one CPU, is try to be run isolated, and some random task starts to decide to run this worker on this isolated CPU, then it basically would either starve if the priority is lower, or preempt the RT task, which is also not what we want. And so these are a few things that should be avoided while using the dispatching work for later mechanism. All in all, I tried to summarize how it works and what should be avoided in order to not to break RT in big time. So basically, avoiding raw spin lock T and sticking with spin lock T if it's possible, because the former one would actually disable preemption and interrupts. And this again will lead to higher latencies, which is not what we desire in the end. Also, if one does explicit lock disabling interrupts or preemption, he should be aware of what he is doing, and that this, in the end, especially if the items or the latent or the section is unbounded, would also lead to high latencies. Not to mention the global spin locks or raw spin locks, which are visible in all CPUs and could be acquired more or less at the same time. One thing is also important: if one comes around and creates new primitives for polling, completion, or whatever, you should be aware that for RT, we would need some kind of handshake to make sure that the primitives are not polling and forever and gets preempted from one side to the other. And the last thing is basically avoiding SoftIQ callbacks if possible, basically for the limitations that we have. And adding more there will basically hurt the runtime in general. And yeah. And this is basically it. I'm done. Do we have any questions?
Yes, you have some questions in the chat. Are you able to see it, or would you like me to read them out for you?
I could stop sharing and then I could basically see it, I guess.
Okay.
There we go. What are some ways one can find code paths that don't play nice with RT? Basically, that sleeping while atomic is a good one, because this will see if a sleeping lock is acquired where it's not possible. The other thing is if you test and see that the latency goes up. And this is all that comes to mind right now, because these are the things that are hurting us. When do you anticipate the PrintK issue would be resolved? In the meantime, doesn't that create a large and unpredictable worst case response? I don't know exactly when PrintK will be solved. It's being worked on and discussed. As for the RT tree, we don't care that much because we have out-of-tree patches which basically solve it. So we have the printing thread, and we wake the printing thread from the atomic context. So the RT patch set is fine. We only need something for upstream, basically upstream solution that we have for most other things. And yes, config debug atomic sleep is the one, yes. Are there any compliance tests that ensure a RT driver is RT clean? No, we don't have this. Basically, if the debug code does not complain, this includes sleep while atomic, this includes logdep in general, and if the driver doesn't increase any latencies or lead to any increased latencies. So what we saw in the past with GPU drivers was that they were cleaning caches immensely, and this led very quickly to high latencies, and this is not desired from RT point of view.
So what's a baseline latency, you say, beyond that? That's my question linked to compliance test. If we have a compliance test that says, runs and says, well, if a driver or a user space activity exceeds this threshold latency, then you can say it's not clean and you could go look at it. So what you're saying is you don't have one and you have to turn on, maybe first config debug atomic sleep and run your code paths through, and then turn that off potentially and check the code paths to see baseline, get a baseline latency and make sure that latency is not going up.
More or less exactly, yes. The baseline latency is also very dependent on the hardware you're using.
Right.
So for instance, what we saw a lot are, for instance, BIOS implementation that do memory scrubbing, especially the server system, the big ones. And there we see that sometimes the CPU is vanishing into BIOS for 10, 20, 50 microseconds or even more. So this is not basically the driver problem, but this is a system problem. And this is also something we want to disable as much as possible, including the CPU idle implementation, which also sometimes clear caches and go to sleep for a long time and need then millisecond or half a millisecond to wake up again.
Mm-hmm. So you're referring to maybe ACPI, going into ACPI or BIOS and doing rescanning perhaps? How would you eliminate that? It would be difficult. Say if you have to rescan the bus and that goes into ACPI layer.
So for Intel, there is CPU power tool, which basically tells you what low-level C-level for CPU idle are available. And you could disable all of them except for C1, which is the lowest one. And everything higher, you could just say, no, I don't want to. And for the BIOS thing I mentioned, I think Dell has a few options offered. What in a document, they say you need to do this, this, and that, and then this memory scrubbing vanishes. But from a, come again,
so
please?
do you have any kind of document that talks about all of these different findings that you have had, Dell, and what to do and how to make sure that your hardware is set up right for ideal RT performance?
I don't think we have all of these. I think if you look for PremRT and Dell, then you find a document that has been released by Dell itself, describing which option needs to be enabled or disabled.
Okay.
But other systems are basically depending on the vendor.
Okay, thanks.
Does the PPT introduction about the how to not break PremRT base on PremRT patch? Does the PPT? I don't get this one. Could this be rephrased, please? I'm just struggling with the last question in the chat, actually.
So I'm thinking is I think this PowerPoint introduction, I think is what the PPT stands for. In your introduction about how not to break, does it refer to having the preempt RT patch enabled? I believe that's the case, but.
Yes, actually, yes, that's the case. Right.
I think that was my interpretation of that question. But if Yun wants to clarify, that would be fine. That'd be appreciated. Well, if there's no more questions, I'd like to say thank you very much, Sebastian, for doing this for us. And very much appreciate the information. And yeah, we've got some thank yous starting to show up in the chat. Oops, looks like, yes, okay. Looks like we've got one more question in there. RT is used in DOM-U, but not in DOM-0. How does it work?
I don't see that one. Come again, please, Dom.
DOM-U, but not in DOM-0. How does it work from Seb?
I have no idea how it works on Xen.
Yeah. We might want to try to connect up with Stefano and have that discussion at a point in time. In the systems working group, this is the sort of topics we talk about. So I don't know. I think I saw earlier, I think I saw Philip here. So this may be something we have a discussion about in the system working group and reach out to you for more information. Yeah.
Okay, okay.
Yeah, so using Xen. Yeah, Seb just agreed it's using Xen. Okay. So we've got some more homework after this. Okay, very good. Some more things to figure out. But again, thank you very much and appreciate your sharing this information with us. Take care.
Yep. Thanks. Bye-bye.